Hi, I'm Jonathan with the Chrome GPU Metrics team. Yesterday during his lightning talk, Badad mentioned we're going to go into detail on how you could use the traces and tooling that our team has been working on to diagnose why you might be experiencing drop frames or jank. The two of us worked together on putting this presentation, and thank you for joining us today. First, we need to have a quick recap on the life of a frame. This encompasses multiple processes and threads, with a vsync originating from the GPU process that's passed up to the render process, where two main threads are of interest: the compositor thread that handles smooth animations and scrolling, and the main thread that does the vast majority of the work of Blink, your layout, your JavaScript handling. Both of those threads are responsible for creating a compositor frame, which is sent back to the GPU process. And often it's actually the main frame that is running behind, which leads to a staggering output from Chrome. The GPU process takes the aggregated surfaces from the different renderers, such as the main frame, various iframes, as well as the compositor surface from the browser's top UI controls, and puts this together for what's actually displayed out to the physical GPU. All of this is encompassed in the pipeline reporter. This is the central trace event that we're going to be talking about today. As you can see, visualized left to right here, the pipeline reporter encompasses all the different segments of the life of a frame that normally cross multiple processes and threads. Here you can see that we have the breakdown of the pipeline reporter staged vertically, and each of the breakdowns it represents is going to be in order left to right when we look at a trace, but here they encompass the life of a frame in the chronological order from start to finish. Typically, these end up overlapping in traces as frame production happens across different stages in parallel, especially as latency starts to build up in parts of the system. This can be quite complicated to look at and investigate, but we're going to take a look at a few more fine detailed examples today. The first thing that helps us figure out why we might be impacting smoothness are the args of the pipeline reporter. These are encompassed in detail at the bottom of the trace detail view. Firstly, the frame sequence number is the incrementing counter related to which frame we are in order. This is important for when we're dealing with split pipeline reporters. Next, we're also looking at the states. This could be if the frame was dropped. Presented all is when the main thread was able to completely get its frame outputted, either A, with the compositor thread on time, or B, at a later point in time. Presented partial is used when the compositor thread itself was able to submit its portion of the frame, but main was able to be ready on time. And no update desired represents when we started a frame and we thought at the beginning of the vsync that we wanted to actually produce content, but partway through the production we realized we actually had no visible changes to make at this time, and so we stopped. Other aspects that are encompassed in these details are the scroll state, so which of the two threads is responsible for the scrolling, or if no scrolling has all occurred during this frame. There's also a series of flags impacting the smoothness. So this will be things such as if there's compositor main thread animations, if there's missing content, or if there's other input that we expect would actually be impacting smoothness. The most basic case for a pipeline reporter is when there's no overlap whatsoever. For this to occur, when there's a main thread work to be done, the main thread has to be relatively fast. It has to be ready before a certain deadline that the render's compositor thread decides. In this example, you can see that it's too small to see here without zooming in further, but send begin mainframe to commit stage was actually really fast, less than a millisecond. Here we have presented all, and both threads actually had an animation to occur, and it was able to get both within the same single thread, so there was no latency to either animation in this. For overlapping pipeline reporters, things get a little more complicated. So here, before we look at our particular pipeline reporter today, there was a small idle frame. So Chrome hadn't been doing anything yet. So when it started trying to produce frames, unfortunately, the main thread was unable to be ready in time, and so we denote this by splitting the pipeline reporter in two in the trace. One is going to be representing the amount of work done on the compositor thread and when that frame was submitted. This would line up with the presented partial, whereas the main thread frame will take longer and will end up being incorporated in a later frame and visual update. So if we zoom in here, you can see that the pipeline reporter that's associated with the compositor thread, it has presented partial denoted at the bottom. It's also denoting that it was handling an animation, so this is something that would affect smoothness. And its frame sequence number is, in this case, 359. When you see a split pipeline reporter, the actual frame sequence number is going to be repeated in both. And as I was mentioning, the presented partial will only be on the compositor side of it. Another way you can tell is when you zoom in at the little breakdowns in here, there'll be no commit related breakdowns if it is the compositor only side of a pipeline reporter. If we look at the main thread, in this case, you can see the send begin mainframe to commit is here. It has the same sequence number. And this one is presented partial, meaning it eventually presented completely. It was not dropped. It's just if you see from above here, it took effectively 2 vsyncs to be done. And it was fortunate in the case that for the user, there was no main thread related smoothness aspects. So this one negatively impacted their experience. One way you can also tell if something is affecting smoothness is another trace event called tracker validation. These are going to be long-running slices across your trace that denote when different forms of animations are happening. Animations, wheel scrolls, etc. They'll all be denoted under the name here. And in this case, you can see there's a series of different tracker validations. Some of this was rafts, some of this could be JS animations, and some of this was wheel scrolls in the particular trace we took this from. Other aspects that this includes is how many mainframes were reported because we decided there was no work to be done or it was unavailable in time, and as well as how many times the main had an update ready, but there was actual no visual damage. This can be, for example, if main thread is doing work that ends up being outside the visual rect for the user. Next, we're going to take a look into drop frame alerts as well as some jank. We're going to do a dive into traces to show you kind of live how it's done. But in case you like to follow along after the fact, screenshots of all the important aspects are going to be included in the slides for you. At the top of every trace, there is this alert track up here, and it's where we're going to actually find drop frame alerts. But it only denotes the frame alerts that are affecting smoothness. So here on the left, we can see that the frame was dropped and that it took 16 milliseconds. So we realize this within a single vsync. I can hit the highlight key, which is M on the legacy trace viewer, and then I can scroll all the way down to a render. We can see something's highlighted. So if I zoom in, I can see this pipeline reporter here is dropped. If I click on the actual begin impl frame to main frame, see it's also dropped. Out of curiosity, if I click on the one to the right, it also was. And if I scroll all the way back up, that is the one that lines up with the second drop alert. So if I zoom out here, one thing I can also note is that here on the left, there's a few slides that, or there's a few trace events that look very similar. There's 3 other events, and each one of them was also dropped. But they don't have any drop frame alert above them. Why is this? Well, in this case, none of them were denoted as affecting smoothness. If you're trying to figure out why that is the case, we have another trace event called the tracker validation. Tracker validation will show you what type of event is currently happening that's affecting smoothness, such as, in this case, the dropped alerts that we run into are main thread animations. And tracker validations will track other things like compositor animations, rafts, JS animations, and scroll events when those actually start happening. So at this point in time, we're looking at ourselves having 3 trace events here that aren't affecting smoothness, and then 2 that are. So what's happening with these drop frames? How can we figure out why they're dropped and why they don't affect smoothness? Well, if we scroll up, we see above them that the main thread on the render is really busy doing layout. This can take a fair bit of time. In this case, a bit under 66 milliseconds. So this means that the main thread wasn't done preparing content for the compositor thread to even display. And if the compositor thread doesn't have previous content to display or an ongoing animation like a compositor animation, it's going to be unable to produce frames. So during this period of time, we're still loading, we're still doing the layout, nothing's ready for the user yet. This is why these don't affect smoothness. Next, let's try to figure out why these frames that are affecting smoothness were dropped. So if we look above them, we see this very long-running pipeline reporter. It's running for almost 100 milliseconds. If we take a look at its content, it is eventually presented all. As we can see here, it has a send begin mainframe to commit. Although that starts quite late. It's starting almost an entire vsync after the begin frame first arrived. If we scroll up, we can see that this is because layout was still occurring at that point in time. But that doesn't explain why the rest of this frame was taking so long. So for that, let's scroll all the way down to the GPU thread. First, we can see here that the GPU thread is actually quite busy on its main. Unfortunately, the trace I took was from the perf dashboard, and it didn't have some of the extra categories on that would let me figure out exactly what was going on here. If you were to record your own custom trace using rendering as a default tag, things like GPU and benchmark and other interesting categories would be on by default, and then we would probably have more information here to debug the root cause. Another thing we can look at while we're here in the GPU process is if we scroll a bit further down, we can see this interesting trace event called graphics pipeline draw and swap. This denotes the total amount of time that the GPU process was spending converting the compositor frame into draw commands for the GPU, as well as the amount of time spent in queued waiting for swap to start, which is when we're actually going to be swapping out to the physical hardware. So in this case, you can see most of the time it was waiting for swap. This reason for that can vary depending on different scenarios. Sometimes it can be we aren't vsynced align. Sometimes we could be waiting for another dependency. In this case, it's because main's blocked, but we currently don't know why. If we're interested in other things, we can see, for example, that the viz compositor thread itself, which is responsible for receiving the compositor frames from the renderer and then preparing them for main, is very idle during this time. So all of the busy work is on main. If we go back up and look at the renderer, we'll also notice that there's a second pipeline reporter below it that is also very long running. This one is also denoted as presented all, but it is a higher frame sequence number 34 versus the 33 that we saw above. This one, though, if we look, has only the begin impl frame to send main, but it doesn't actually have the main, and it doesn't actually have any commit in it. This is because the previous compositor thread frame was dropped along with the main, and since this main was long running, this is the first time the compositor thread will be actually contributing its portion of the updates to a visible update. Here you can see that the swap and presentation for both of them occur at the same time, meaning there was one solid compositor frame from these two that was submitted to the GPU. When we haven't had a compositor frame successfully submitted and presented, we won't have been received the acknowledgement that it was presented. So during this time, the other begin frames that we're receiving are going to be dropped by the renderer because we're unable to actually receive the acknowledgement and produce the content in time. So that's why these are dropped. But because, as we were mentioning earlier, there is the main thread animation, it will affect smoothness. The user will perceive something wrong, something jittery on the animation here. So another trace event that I want to talk about is the janked events. These is an entire row of trace events that you'll see, and it will denote the time at which there is a significant change in the amount of time we were required to produce frames. So if we look at this one here, we're going to have a jank event here, and it's taking effectively two vsync intervals, and it's related to a compositor frame animation. So let's take a closer look at what's happening. If we zoom in here, we can see that we had several pipeline reporters that are all taking a single vsync right before. Everything was running nice and smoothly. But after here, you start to see the overlapping pipeline reporters that we were talking about earlier. This is usually symbolic of like when there's latency in the system. So looking at how the jank one lines up, this pipeline reporter here is the first of the two vsync interval pipeline reporters. And if we check, it is presented partial, meaning this is only the compositor side of the frame that was expected to start. That lines up with the fact that the jank itself was denoted as a compositor animation. So what we want to find out also is what happened to main during this. So if we see frame sequence 103, and since this pipeline reporter started at the same time, it's likely the matching main thread one, and it is 103. Fortunately, it was able to be presented all later. So what's happening here? Well, if we look first of all, the main thread is really busy during this point in time. It's spending almost an entire vsync for every single begin main frame. Why it is, I can't be sure from how this trace was recorded. I'm missing a few categories, but that would be explaining why that one's taking so long. However, what it does not explain is why the compositor thread is taking so long. So if we look at this, we see that we're spending almost 16 milliseconds on the first part where we're sending the begin impl frame and waiting for main. This is a bit surprising because it means we aren't giving up waiting for main early on. It means we aren't even attempting to try to submit the compositor side until almost a full vsync. So could something else be happening and affecting this? If we scroll back down to the GPU process, we'll see here that there's actually a gap in time along the draw and swap period. This means that we actually completely skipped submitting a frame. That lines up with the jank, but it's still confusing why it happened. So one thing I'm going to do here is I'm going to enable flow events. These are trace events that go between different processes, and they can give us some very interesting insights. The viz ones, for example, actually track various interesting events, such as when the GPU process sends a begin frame to the renderer, and it can also track when the renderer frame arrives. So here we can see the received compositor frame. So if we follow the flow events up, you'll see where they'll line up with the compositor thread directly above us in this gap. So if we see here, here's where the onBegin frame was received. And here's where we finally actually produced and submitted a compositor frame. And unfortunately, this is a full vsync later. So what ended up happening in this case is Viz is properly sending the begin frames and accepting the frames from the renderer. But in this particular case, the compositor thread just took too long before it started creating and submitting that thread, and so we ended up missing the opportunity to perform a draw and swap. This is actually an issue with the CC scheduler, and we filed a bug, so that we're going to look into this further to try to prevent this particular case happening. But this is an example of how you can look at a trace event, find the problem, file the bug, and then we can make sure to fix it so it doesn't happen. And so those are the traces we're going to look into today. So at this point, does anyone have any questions?